Okay, 1, 2, 3. So we can start. And today we will talk about automatic refactoring of your code base. So my name is Andrii Rodionov. I'm from Ukraine. Maybe we have met with you 3 years in a row. At this conference, I am talking about distributed systems, rough protocol, low-level stuff. But this year, I changed the company and I changed the topic of my talk. But I will also find the place where I can mention my previous company, Hazelcast, and we will see in a few moments how it could be mentioned. So for now, I am a software engineer in Modern. Please don't mix up Modern with Moderna. Moderna is, you know, the antivirus, not the antivirus company, but producing the vaccine against COVID, and they are saving lives. Unfortunately, we are not saving lives, but we are saving your times for more cool stuff. How we can do, but in the way that we are trying to eliminate you with maybe boring job. So what is about the company Modern and what we are doing? This company is behind the OpenRewrite platform or product. Who know what is the OpenRewrite? Who have used it? Are you lucky? So if you don't, please come up after the talk and we will talk with you. Okay, that's why I will start my talk with explanation what is OpenRewrite and how it can be used during your development cycle and so on. So OpenRewrite is the open source product or platform for automatic refactoring and code migration that you can use to migrate your Java code and in the future not only Java code. So what we can do, we can deeply understand and read your code base, understand formatting, types, and so on, and apply some migration recipes to modify its code base to move it to the new version, new framework version, and so on, and preserving the original style of the code base. We have around more than 3,000 of different migration recipes for Java, and not only for Java. That allows you to apply different transformation, common framework migration, security fixes, static code analysis, also dealing with configuration files, YAML, and so on, and also build system, Gradle, Maven, and so on. So a lot of stuff around this. This product was founded by Jonathan Schneider when he works at Netflix, and Netflix has a huge code base and has a problem that it should be migrated to the new version of the internal framework, new version of Java, and so on. So Netflix decided to build some tools that should help to do this thing and to do this stuff. So that's why how the OpenRewrite was born. Then it was outsourced as a public open source product, and on top of this product, the Modern company has been built to provide some additional things and additional tools that I will mention with you. So let's start with example how we can use the Modern platform or OpenRewrite tool. And for this, I decided to take my previous job, Hazelcast, and decided to migrate in real time it from Java, Java 17 to Java 21 with one click. So for this reason, I will run so-called recipe Java migrate upgrade 21. Before using of OpenRewrite, we had a separate dedicated person in our team, and this person several months migrating our code base from Java 8 to Java 11, then from Java 11 to Java 17, and it takes a lot of time of his work. So for now, I can do his work in 3 minutes. While this migration is happening, let's try to understand what is behind this command, upgrade to Java 21. And behind this command, we are running a set of recipes. So it's called migration recipes. And it consists of a lot of some sub-recipes. So for example, we are trying to migrate to Java 17. Java 17 applies different rules for migration, different parts of constructions, instance of, text blocks, string formatter, and so on. And if it's find that code base is not Java 17 yet, it's trying to apply recipes for migration to Java 11 and apply all rules to migrate from Java 8 to Java 11 and so on. So in this screen, you can find this strange graph, and it is the recipes and how it's connected to each other. So it's, as for me, it's more for fun stuff than for practical usage, because it is hard to understand what is happening there. And each of these recipe is a separate sub-program that you could write and you can extend. For example, to migrate to Java 21, we are running around 100 of, not 100, 1,000 of recipe. So let's see, let's take a look how migration happens. So it's almost finished. So we are writing the results. And after migration, it will be generated the patch file that we can apply to our code base, and after this we can review each changes that OpenRewrite made with your code base. We can look at these changes here, but firstly we should apply those changes. Yeah, apply. So by applying these changes, we will see how many files it proposed to upgrade, update, and can review each of the changes that it has applied. And now, yeah, I hope you can see that is about 100 files has been changed. We will not review all of these changes, but let's take several files to look what changes OpenRewrite proposed to do during the migration to Java 25 or Java 21. So one of this file is jar on client validator. And yeah, what we are trying to propose to do, we are propose to change path to the path of, also propose to change string format to the new formatter, and yeah, for this file it's all. And the next file I would like to show is a plan executor, and for plan executor there are more changes, and these changes is related to, you can now use get first, not using get zero, and also have some benefits from instance of, where you could declare the variable if it instance of, and then use it, then manually convert this type and declare a new variable, and it is the same. So, and it's applied for all our code bases. Yeah, but the question is it compilable? Is it, can we trust these changes? And to verify it, let's try to build Hazelcast with Java 21. So it's the canary test. We will not try to run all integration and other unit tests, but it will be the first test. While this test is running, we can talk a little bit about how this upgrading works under the hood. When I run the command run recipe, I am a little bit cheating with you, because actually we are not working directly with the source code and apply recipes to the source code. We are doing and working on some internal code representation, and this code representation is named LST tree. So on the first step, to be before running the recipe, we should build this LST tree, and this is done by from the CLI command by mod build. What is the LST tree, and what is how it looks like and how it's doing? So we can later on check if it compiled successfully. And yeah, what is the LST and how it looks like and why we need it? So when you have the source code, what the usual compiler do on the first step? It transforms it to the abstract syntax tree, AST tree. But this tree is not useful for code manipulation and code refactoring if you would like to preserve your formatting and apply some different recipes or rules on top of this code base. Because the AST tree has a lack of information about formatting, it doesn't preserve it, and it also lacks the information about semantic code behavior and about the type system. So what we decide to do, we decide to add to the LST tree information that metadata that preserves all formatting, all spaces, all comments, all new lines, all code structure, and also add information about types that used in this code base. A little bit later, I will explain what is the type attribution and how it looks like. And by adding this additional information, we have the so-called LST tree, lossless semantic tree. And the number of additional items or subnodes that added to this tree is very huge. So what is the LST tree? LST tree is a model that's specific for a particular language. And it represents any data structure or any construction that this language has. Also, it preserves the information about formatting, as I mentioned before, and it also preserves information about types that used in this code snippet or in the whole code base. If it is most understandable what formatting is, it is maybe not very clear why we need the type attribution and what is this. For this reason, let's discuss the small example. Let's take this snippet of the code, and when we convert it to the LST tree, information regarding my comments, spaces between every keyword, the names of the classes, modifiers, and so on, will be preserved in a so-called syntactic part of this LST tree. So it preserves information how this source code looks like. But this information will be not enough if, for example, you would ask the system, let's find all classes that extends or implements runnable. Because for runnable is not present in this code snippet. Runnable is present in a thread. So thread implements runnable. So if you would like to find all classes that implements runnable, you will not able to do this based on the standard AST tree representation. That's why we are adding this information to our LST tree by doing some strange procedure called type attribution. What we are doing is, we use Java compiler information, Java compiler internal tools, Java reflection, to get this information from the compiler internals. So we are analyzing all classes that our class extends, for example, class thread. Save its type, what it extends. Also, we start analyzing class thread information, all methods that present in this class, all arguments that class thread has, and also every argument, or every type of this argument also will be analyzed, and what this argument extends, what it implements, and we'll also add it to the LST tree. And finally, we find that thread implements runnable, and for runnable, we take information what method runnable has and what annotation it has. So during the stage of building LST tree, you need that all dependencies will be available during this procedure. Otherwise, it will be impossible to make the type attribution. And this information will be later used by recipes to find different methods that implement something, extend something, has methods with specific arguments, and so on. So it will help us to write the correct recipes. In terms of how it looks like, LST tree, if we are taking the debug information and taking inside the LST tree, this is our class declaration. This is the information that this class is public, that is type mine thread, that this class extend thread. So its information, it is more about formatting, because you can find here spaces, markers, comments, and so on. And additional information about the types of this class and all included classes is are present in a type attribute of this LST model. The type provides us information about that this class extends thread, and thread also implements runnable, and runnable, for example, has some methods with arguments, that the runnable has annotation, and so on. So if you would like to add the new language support, we should do two things. We should analyze how code and preserve how code looks like, and information about the type related to every object in our source code. After this, we can build for each source file, so-called the LST tree. The LST tree is a composition of subtrees. And yeah, it could be represented like this one. And after this, when we have this LST representation, we can visit all these subtrees, all sub-elements, and could analyze them, or later on we can modify them and produce a new LST element or node of this tree. But it will be the next step. So by running the LST transformation, we transform our source code to our internal representation. What we can do with this internal representation? We could analyze it, but we also could do another interesting stuff. For example, we can print it back to the source code. Since this LST preserve all information about formatting, and preserve all information about types, but types is not necessary for this. We can print it back from the LST tree to the initial source code. And this source code that we are printed based on the LST representation will be or should be identical with the initial source code. So when we are writing the LST parser, so we are writing this parser, to check that the parser works correctly, our tests, we have a bunch of tests that verify that any language structure will be printed back in equal view as it was before the transformation. So when we are building the new parser for new languages, it will be the first step to verify that our parser works correctly. So that is the LST representation. And with this LST representation, we could convert our code to LST and can print it back to the initial source code. But in addition, we could do another interesting stuff. We could run some transformations based on this LST tree. And after this transformation will happen, we can try to print it back to our source code. So this is some transformation. And these transformations is called recipes. So all our recipes are based and works on top of the LST tree. It's apply changes to this LST tree, change the nodes, the types, adding nodes, deleting some nodes, and then print it back to the source code. So what is a recipe? A recipe is a small program that have access to all internal types with type attribution, all formatting information, and can modify it. And it works, as I mentioned, on a LST code representation. It's use visitor pattern. So if you are worked with some XML parsers, yeah, you could be familiar. It was some visitors parser before. And when you can visit every element in the XML and could analyze or modify it. So we use the same approach, and with this approach we visit every element in our tree and could modify it or change it. So these elements will be classes, methods, fields, and so on. How this visitors method looks like? It looks like something like this. So to write the recipe, you can implement your own recipe by extending our recipe class, and then you can override visit statement, visit annotation, visit class declaration, visit assignment, and all data structure construction that you have in your LST model. By default, this method in a base visitor not modifying something and returns the existing node element back to the from the visitor method. If you would like to change something, you can override this method and implement your logic for modify this particular element. For example, if you would like to parse this expression, list of AB, at first place you will visit expression. So expression will be on the top and represent list of A and B. Then the visitor will go in deep and visit method invocation. So the method invocation will be off. After this, it will call visit identifiers. It is the first identifier, and this is the second identifier. And as our identifiers are literals, it will call visit literal. And if we decide to change A and B, for example, to I don't know, C, D, we should after this return from our visit literal D instead of C, and it will change our LST model. And when you print this LST model back to the source code, in the source code you will have another literals. So let's take a look on some simple recipes. How it's looks like. Yeah, by the way, you can see that Hazelcast compiled successfully after the migration. That's why you can trust our OpenRewrite. Okay, let's take a look for some simple recipes. I've implemented these recipes around a couple weeks ago. So to start with recipes, it's simpler to start with unit test. And with OpenRewrite, it's very encourage you to do this in a TDD way. So you are writing the test that will show how recipe should change your code. And then you are writing recipe until it starts working, until the tests start passing. So in this recipe, what we would like to do, we would like to replace has size this existing method has same size as. So to eliminate some additional code structures. How we can do this? For this, we can write the recipe, and what this recipe is doing. It extends from the recipe class, as I mentioned before, and it looks like it overrides the visit method invocation, because we would like to find has size, and then change this method has size, replace this method has size on a method has same size as, and also delete the method invocation on argument, and to put this argument as it is without method invocation. So in this recipe, we override method invocation, and we have the patterns that will check if this method is has size. Yeah, has size. So we step into this visit method invocation. If it not much, this pattern, we return the existing method and going to another visitor classes. But if the matcher is successfully, we are analyzing is it possible to make changes, and after this we update method invocation by introduce the new method name has same size as, it is also the constant, so and return this updated information about this method invocation to our source tree and to our LST model. Another simple example is to move from JUnit 3 to JUnit 4. And for this reason, we are trying to replace rule public timeout on annotation, timeout something. And we also use the recipe for this, but in the previous example, we use we should override visitor for method invocation. Yeah. And for this recipe, we should overwrite variable declaration on the class level, and then add something to add additional annotation on a class level. So in this recipe, we should implement several visitors. One of the visitors will examine class declaration, and another visitor should examine annotation. And to add a new annotation, we use so-called Java templating. It is also our internal implementation that you shouldn't modify the LST tree in a manual way by creating some node with class providing all additional information, like formatting and so on. You can use a string template, and this template will be automatically converted to the LST representation and will be put it into the right place in a source code. So it's all happened on LST representation. That's how it works. So at the first glance, the recipes could look a little bit strange, yeah, but if you are starting to write this recipe, you will be in some point of time a little bit familiar how it happened. And we have the huge number of recipes, more than 3,000 of recipes for a lot of stuff. For example, for common check style analysis, for example, if especially it's the case for big banks, companies, and so on, if your manager would ask you eliminate or fix all sonar issues, you can you can run the recipe that will fix all sonar issues. So we have a special recipe for the most common sonar check style problem, and it will fix it, and the manager will be happy. Also, check style violation, migration from Java version. So yesterday I found that we already started work for Java 25 recipes in our repository, so we should be in time. Also, it's about Spring Boot migration, Micronaut, Quarkus, Self4G, JUnit, and many others. And all this recipe, it's not built, not of all this recipe has been built by our company, OpenRewrite. Most of this recipe has been written by community, and they're open sourced. But company, for example, that has some internal frameworks and so on, use this product to write their own internal recipe for their internal frameworks or code-based migration. And yeah, we have ecosystem that could be split by different recipes that supports languages, frameworks, libraries, tooling, and also some infrastructure like JSON modification, Maven, Gradle, and so on scripts. So that was about introduction to the OpenRewrite and how it's look like in a Java site. What about adding the new language support? In our current pipeline, we are trying to provide support for 3 additional non-Java-based languages. It is Python, C#, TypeScript, and JavaScript. For each of these languages, we should define on the first stage the LST model. So how this language syntax can be converted to the LST tree representation. For all those languages, TypeScript, Python, and C#, we already defined this model. Then you should write the parser. The parser writing in a manual way, so you could take information from the AST tree that represent that could be taken from the compiler of each of this language. For example, for TypeScript we use TypeScript compiler, for C# we use Roslyn, and for Python we use Python compiler. And then we base it on this AST representation. We are trying to build, to fulfill the LST model for each particular language. As for formatting, it is quite pretty well, except the Java, because the Java compiler not provide you information about Java code formatting, and for this we are using very dirty way, so substringing, regexp to analyze Java source code and find how many spaces between different elements, what is the comment, what is the new lines, how many new lines between the next statement. So we are doing this manually based on Java source code. For Kotlin, it is maybe the best compiler. So it provides you full information and full insight about the C# code. The worst compiler is Python. And with Python compiler, we are not even able to take type attribution. So now we are looking some additional stuff for some specific library for Python where you can take this type information. So in terms of type information and type attribution, C# is mostly done. With TypeScript, we are working on this. And this is the current stage how we providing support for new languages. Then we should implement the recipe execution engine. It's include a lot of utils that you could use during the modifying LST elements, because in a raw way it is very inconvenient to do so. You should provide some templating mechanism where you can write the code snippets that can be put it into the new LST tree and so on. So it's a little bit tricky work and consuming and will consume time. And after the execution recipe engine will be implemented, only after this we can start implementing some recipes for the particular languages. I will show a quick example about how we can implement the recipe for TypeScript. And for TypeScript, the recipe will be implemented in a TypeScript. So we have the test, and this is TypeScript code. And what this test will check, that if we have in the class with method, the recipe will update this method to some new method. So method will change the name. And for this reason, we implement replace name recipe. How this recipe look like? It is very simple. So we extend the recipe. So the recipe, it's not the Java recipe, it's the mirroring re-implementation in a TypeScript language. So if you would like to provide support for another language, for C# or Python, you should re-implement these execution languages, all the recipe concept in a dedicated language. So in TypeScript, what this recipe will do, we should override visit method declaration. And if when we are visiting this method, we replace the name of this method to the new name. How the internal LST tree, for example, for TypeScript look like, we can see by setting the breakpoint here. And if I run this recipe, I hope you can see, yeah. So we can see that we have the JS compilation unit, and we have statements in this LST, and the statements is where is it? It's class declaration statement, and inside the class declaration statement we have the class name, and also we have where is the body of this class, and inside this body we have the statements, and one of the statements will be method declaration, and in this method declaration you can find the method name, method name. The name is M, and so we can modify this name. So for type information, it's not yet implemented yet for TypeScript, so the type unknown. So we continue to work with this implementation for the TypeScript. But all recipes that not demand, for example, type information could be already written and could be applied for the TypeScript. So it's yeah. If I, for example, change a little bit my test, for example, specify not the wrong name, you will see that the test failed, and you will see that the expected result is not equal to the actual result. So in this way, we are also provide and write tests for all our recipes. When we are writing recipes, our first rule: don't harm anything. So if we are not sure is it straightforward recipe or is it in some way harm something, we are not doing this recipe or make it this recipe not a part of the bundle, but as a separate recipe that the people can use it by their own and decide. So by at the end you will have the bunch of changes, and you can review each changes and apply or decline these changes in your source code. Yeah, but our first rule is don't harm anything when we are thinking or writing the recipes. This is cool stuff, and going in this way, actually, we should implement all recipes, all the new bunch of recipes for each of these language. But the problem is that when we are finishing our LST model with new languages, finishing parsers, recipe execution language, we'll have the situation that there are no recipes yet for those languages, because nobody haven't started write them. And the recipes, maybe it is the most useful and our treasure of the OpenRewrite, because without recipes, you will not able to use OpenRewrite for other languages. For Java, recipes has had a long history, and to have more than 3,000 of recipes, it takes, I think, 5, 6, or 7 years to have this number of recipes. But we don't want to wait and put all our resources, all our engineering stuff in writing new recipes for for new languages. We are trying to doing it in a little bit smarter way. When we are building LST model for the particular languages, we have found that a lot of data structure of this LST model are the same in different languages. For example, method invocation, class declaration, method declaration, some variable declaration, and so on. So we can reuse this core part of the LST model, we can reuse it in other languages and create only the LST model for the particular languages for those elements that is not the same in a Java language. But having the same LST model for different languages, we could also reuse the existing Java recipes to run on LST model built for another languages, not Java languages. And for OpenRewrite, we come to the Java principle: write once, run anywhere, or debug anywhere, or fix anywhere. In terms of OpenRewrite recipes, it's definitely, we couldn't use all Java recipes for TypeScript, but a lot of recipes can be reused. For example, static code analysis, formatting, and so on, method replacement, method declaration replacement, method invocation replacement, and so on. So for now, we are going in this way and what we are trying to do. For foreign languages, for example, TypeScript, Java, script, Python, and so on, we are building the LST by using the compile parser from native language parser. And then we serialize this LST tree and send it to the Java. In Java part, we deserialize this tree in a Java LST tree representation. And after this, we can use Java recipes to modify this LST tree. And after modification of this LST tree, we could serialize it back and send it to the native language. So for this serialization, we definitely define the protocol, mapping how each data structure will be mapped, serialized, and so on. Yeah, but we almost done with this. And after applying these recipes, we can put it back to the non-Java languages. So this is our idea how we can reuse the whole bunch of existing recipes in new languages, and we are working on its implementation. So that's almost the end, but the last slide, it's about what is the difference between OpenRewrite, that is open source, and our company Moderne platform. So talking about the OpenRewrite, it is completely open source project. And for this project, you can use command line tool, you can use Gradle plugin, Maven plugin. It's also used in Amazon Q, also Spring used in Broadcom in the Spring Migration Advisor. Also, we have the JetBrains plugin. That could help you with code migration. Also, we have a bunch of open source recipe for majority of frameworks and so on. And talking about the enterprise part of our application, the Modern platform, we have some private recipes here. And also, you will have an ability to use our UI tool to manage your code base and run all recipes in a cloud. Also, it will provide you some insights about your code, and also you can save the internal representation of the LST tree on a disk, because for huge recipes it will take a lot of time to build this LST tree, and if you are not changing your code base very often, it will stay the same, and you can experiment without applying the changes on a cloud platform. So it's the main difference between OpenRewrite and Modern. And that's all from me for this moment. Thank you for your attention. And looking for questions. Okay. Does the refactoring happen offline? I mean, if refactoring code base disclosed sent to external server. Yes, it's happen offline. We have different scenarios of setup. So we can create your private cloud where you can share your GitHub private repository, and it will be only available for you. For those companies that use a private internal repository, we have a separate local installation. But you should synchronize the recipes from our repositories. And all these changes will happen offline. So it's the separate installation called Modern DX or DX. So it's completely offline. Do you need to write recipe in language that is being rewritten? For current moment, yes. But when we implement this LST serialization, deserialization between different languages, you can write, for example, Java recipe on a TypeScript. Because it will work in both ways. So you could send LST JavaScript LST to Java and run the recipes, and you can send Java LST to the TypeScript and then run TypeScript recipe based on this LST representation. So it's our plan for the future. Where to browse list of recipes. It is in our documentation, but if you are log in and registered in our cloud platform, it is also free. You could provide also, this is the list of recipe, or you can find it in documentation. We also have a chatbot where you can ask it, what recipe can I use, for example, for Java migration? And it's analyze our existing recipe base and should provide you an answer and provide the command how you can run this recipe. Is it possible to select only? Yeah, it is possible to select only specific recipes. As I show you, where is the builder? Yeah, you can run the bundle of recipes, or you can run the specific recipes. Each recipe has a unique name. For example, where's the name? You can find this unique name and run only the particular recipe, or you can build your own bundle in a YAML-like file where you can specify all recipes that you would like to run in a particular case. How would you say safely adopt OpenRewrite in tighter banking with recipes gives the best impact with low risk? We have a lot of customers, bank, retail, and so on. And if we provide the support, so if they have some problems, we analyze what the problems they have and fix recipes or modify recipes, but it is enterprise support. A lot of companies use the open source of OpenRewrite, and we have around 10 people in a team who are responsible for reviewing all issues in GitHub that community users sent us, and we are trying to fix them as quick as possible, depending on the type of the issue and how it could be fixed. To tell the truth, when I ran on my previous meetup this migration for Hazelcast for Java 21, it failed, and there are around 5 compilation errors. And during the week, we have fixed all these errors that recipe generated. So besides this, we have here on the modern platform near several thousand of open source projects, and we are running every night LST generation for all these projects. For example, For example, if I would like migration to Java and click run, yeah, it starts running the recipes for those repositories, open source repositories. And if we find some issues, we'll analyze them and fix those recipes. So we have continuous time improving our system. That's such way we extend the trustful for our recipe and our company. Is it OpenRewrite useful for translation between program languages? We have not such task yet, but I have found that we have some COBOL recipes. So maybe if you will have a customers that provide those recipes, it will be possible in theory. But it is very time-consuming to write recipes. So when we decide to write the new recipe, we select the most valuable in a commerce term of sense recipes. So valuable for our business of the company. But community users welcome to write any recipes that you would like. Groovy, yeah, Groovy is supported. Kotlin is supported. Scala will never be supported. Yeah, because it's very hard to type attribution and other to do. And our CTO says that it will never be supported. For all other, Groovy, Kotlin, Java are supported. Can Java recipe can be applied to other? Yeah, I've answered this question. Is LST representation is universal for JVM languages? Yes and no. So we have the core parser and we have some extension for each language for another JVM language. So it's some extensions, but in the core they have the same. Actually, we have inside this acyclic graph, because we are not duplicating type information. If we have visited such type information, we store it inside our collection of types, and yeah, in some way we use this graph representation. And yeah, perhaps last question. Could you please could you please clarify how the correct methods to be migrated as part of a recipe are selected? I don't understand question, please ask me in person. And new language, is LST built by custom parser implementation, or it based on the Java-ST parser? For Java, it is based on the Java-ST parser, but we have built our custom LST model, and we are trying to extend this model, that this model will be universal for other additional languages. So as project started for Java, our first LST model only dedicated to Java. Yeah, related to Java. But when we added Java-based languages, we are starting to extend our LST model, and by adding non-Java languages, we have planned to extend, integrate, scale the LST model to support other languages structures. Okay, could OpenRewrite recipe be integrated as a... Yeah, it is integrated in IntelliJ IDEA, such as plugin, but not as... so you can run a recipe from IntelliJ IDEA, but not yet as a hint system. Yeah, we are not working in this way, but yeah, who knows? So, thank you for your attention. If you have additional questions, please come to me to ask.